now we need non-removability of the Sierpinski gasket presented by Ntalampekos on a paper of Ntalampekos. And yeah.
Okay, good afternoon, guys. So I feel a little nervous because this is actually my first time to give an English talk. So thanks, Armenia, and thanks to the organizer for giving me such an important opportunity. So today I'm just talking about the non-removability of the Sierpinski gasket. And this is based on the invention paper written by Professor Ntalampekos. And I'm from University of US Puebla. And we just first give the outlines, and we first give some background materials, and of course we need to clarify the main results of the papers, and then we give some preliminaries that is needed in this paper. And the third part is that we prove of the main theorem, and the fourth is, of course, maybe the most important is the open problems that we can do in the future. So first, let me talk about the basic materials and background and the main results. So first, we need to know what is the quasi-conformal removability. Just now, my academic sister really gave something about the removability. So I'm also happy to see it again. So maybe we can make a better understanding if it's okay. And so if K is a compact set, then we say that K is quasi-conformally removable if every homomorphism that is quasi-conformal on C minus K is necessarily quasi-conformal on the whole C, on the whole complex line. So just in this picture, we can see that it is the K is the boundary of the omega. Omega is this domain, and then it is quasi-conformal on elsewhere. And if the every homomorphism that is quasi-conformal on C minus K, then we can imply that F is actually quasi-conformal on the all of C. Then we see that K is quasi-conformally removable. That is the basic definition. And then we also need to know that in the planar domain, we also say that quasi-conformally removable inside the domain. It means that any homomorphism of the U, because U is a compact set K is contained in the domain U, then the quasi-conformally removable inside the domain U, it means that for any homomorphism of U, not necessary for the homomorphism of the whole plane, which is quasi-conformal on the U minus K, it can imply that it is quasi-conformal on the U. Then we can see that it is quasi-conformally removable inside the domain. Then for some basic facts that we need to know is that quasi-conformally removable inside the domain if and only if it is conformally removable inside the domain. Just like Abhishek told the day before yesterday, it's just a similar result. It has a very similar logic, I think. It's just quasi-conformally is just equivalent to conformally for the removability inside the domain. And furthermore, a set K is quasi-conformally removable inside a domain if and only if it is also quasi-conformally removable inside the entire plane. So sometimes we think that maybe for the geometry or topology of the domain may not be very difficult. Then we still need to consider that actually we consider the whole plane or the whole complex plane is enough. So then the third thing in this paper is about Sobolev removability. Actually, this is not the main result of this paper, but I also want to mention it here because we can then show a big picture, the whole picture of the removability problem. Then for the Sobolev removable, it means that now we don't use the quasi-conformal mapping and instead to be the WEP removable if any real valued function that is continuous in the whole Euclidean plane that is lies in the WEP Rn minus K also lies in the WEP Rn. It means that its definition of the WEP removable. So this is a very important problem in the Sobolev analysis. So for the open problem, this is the open problem 1. It is founded by the Peter Jones and Stanislav Smirnov in 2000, and it cites that its W12 removability in the pen. It means that when n is equal to 2, equivalent to the quasi-conformal removability. Actually, this paper is based on this problem, but I think for the whole problem, this is still be an open problem. And then we can see the applications of the removability problem. So first I want to say an overarching problem is that can we give a geometric characterization of the removability? It means that we need some if and only if condition for the removability, then we can use them in the other tubes as the tubes to the other fields, just like why this important, why is this problem, why so important? So for the applications, just like the professors told for the last few days, it's just the complex dynamics. For the quasi-conformal surgery, it is by Shishikura and Sullivan. And also it has very basic applications in complex analysis, just like conformal weldings. Just some other guys told yesterday. It's about Bishop, Yonsei, and Rodriguez. And of course, the Sobolev removability is one of the central problems in the Sobolev analysis. This is connections to the problems of density and the extendability of the Sobolev functions. This is by my PhD advisor, Pekka Koskela, and Hapu Rayala, and my academic elder brother, Zhang Yi. So, and of course, nowadays it's very popular for the complex analysis and the intersection to the probability theory, as Professor Jacobian told on Monday. It's just the SLE and the connections to the Gaussian free field. The standing man is just the Duplantier. I'm not sure whether my pronunciation is correct.
Duplantier.
Yes, Duplantier. Sorry, I didn't find the online name. And then Jason Miller and Scott Sheffield. These just do a lot of things with complex analysis and connections to SLE or some more probability objects.
PDE, the solutions of this removability is very important. That's
Yes.
Without any probability theory, classical.
And then just I want to tell the brief history of the removability problem. So you can see that there is almost 100 years of lines to give something about the removability theory. So for the early results, it's Besikovici. I think Besikovici is a Soviet Union mathematician, and maybe
No.
Yeah, this is from Soviet Union, from Kharkov.
yes.
From this kind of thing.
Did he live somewhere else?
No, he was all the time in Soviet.
Yeah.
And also fair Haring.
If I may, even before Besikovic, Hoppe used removability to prove this.
Yes.
His mapping theorem. So for mapping theorem, even it's very important. And a Hoppe mapping theorem onto circles.
Yes.
In the finite case, it's extremely important removability.
That is maybe much longer. In 1920s, I think.
Yeah, I'm pretty even Harrison.
Yes. And for the removability of the compact size, the main result is, as we said, the Jones Smirnov's paper and Koskela, Nieminen, and Ntalampekos, and of course, for the latest result is by Ismailia and Ridi Misha, who just gave the talk before me. I think she is an expert in the Sobolev removability. And then for the complex dynamics object, just like Julia says, the removability of Julia says is just a Jeremy Ken, and also this name I cannot pronounce very well. It's just a Gracic or Gracic and Smirnov in 2009. This is meaning just to give characterization of the conditions that such the removability. And on the other hand, we also need to know what objects is just a non-removability, or we can give some constructions of expressional homomorphism. Then we can see it as a on the side and on the opposite side. For the non-removable sides, it's mainly by Kaufman and Bishop, and also constructions of the exceptional functions is just the Kaufman and Wu and Doherty and Miller in 2023, and Ntalampekos in his paper. And of course, just as Reedy told, then removability is highly related to the rigidity of circle domains and Kopis conjecture. This is the first I knew is just the Young's paper, and of course, for the Malik Young's survey paper is very important, I think, in survey paper in this field. And also Young's Ntalampekos paper, invention paper in 2020, and I heard that this paper is awarded the basic science from my country. And of course, for my PhD advisor, Kai Ayala's paper in 2025, he will give the counterexample on one direction of Kershaw serial. And then we just, as Reedy says, told that there are some basic examples of the removable sets and examples of non-removable sets. So for the main thing we just want to know is that for the all sides of positive measure is non-removable. And of course, just like Bishop's flexible curves with Hostoff dimension 1, as some guys told yesterday, is also non-removable. And the converse side multiplies the 0, 1, close the interval 0, 1 is non-removable. And I think just the Yang Mei will give a standard of non-removable sites, and my advisor Kai Ayala used the Wu's theorem to give the counterexample of one direction of Kershaw's conjecture. So I think this is a very basic idea root from here. And then Kaufman's graphs can be alpha order continuous with alpha smaller than 1/2. For the example of removable sites,
Examples of removable, in what sense removable?
of course, this is a little rough. Mostly, I think it's quasi-conformal removable.
Quasi-conformal.
Yes, and some is Sobolev removable, because just like quasi-circles, they are just a quasi-conformal removable. Yes, and now we just come back to the central problem of this paper. It's just the removability of some fractal structures. So the overarching problem is that what about the size of more complicated fractal structures? So the basic is just like the Sierpinski gasket, Sierpinski carpets, because then this why this is important. Of course, one side is from the fractal geometry and another is from the probability theory. Of course, for the just like the Sierpinski gasket, it has a infinity many complementary components. So this is a basic problem funded by Bishop. That is a Sierpinski gasket quasi-conformally removable. And then the main object of this paper is to give answer the question of Bishop. It says that the Sierpinski gasket is non-removable for the quasi-conformal maps. And then the second result is about the Sobolev removability. It says that all homomorphic copies of the Sierpinski gasket are non-removable for the continuous Sobolev functions of the WEP for P is smaller equal to 1 and smaller equal to 2 and larger equal to 1. So this is two results. Actually, the main result is about quasi-conformal removability, because if we have the quasi-conformal removability, then we can derive the continuous Sobolev non-removability, because we know that the definition of quasi-conformal maps is need to be W log 1, 2. So the main theorem we can see as the theorem 1, and we need this to show the quasi-conformal non-removability.
Can I ask?
Yeah.
Does W12 imply W1P less than 2 or?
It's just the quasi-conformal. It's just implies W12, and W12 implies 1 P is smaller than 2. So, but for P is larger than 2, it's just proven by Ntalampekos and Wu in his preceding AMS paper. So then I can draw a whole picture about the Sobolev removability and quasi-conformal removability of the Sierpinski gasket and Sierpinski carpets. So maybe it's like this.
So the P is equal to two, like, over case, yes?
Yes.
Because you told that for P even was already.
Yeah, it's sold earlier than this paper, but by the same author.
But then when P is equal to two, so essentially you're making that space. There.
Yes, it's just.
Again, it's implied by some, maybe, output.
Yeah, so, first of all, it's about WEP.
So we can get in.
And the particle form.
No approximation, but. Not iteration.
Interpolation.
Interpolation.
Sounds similar, right?
And here, the Sierpinski gasket carpet is not only contains the classical Sierpinski carpets, because the Sierpinski gasket is that we remove the equilateral triangles in each turn, but here it's just remove the squares, and also contains all homomorphic copies of the S3. So it means that I think Mario Bang has a topology characterization of the all homomorphic copies of S3. So this one is more stronger, but for the Sierpinski gasket, for the homomorphic copies, it's not straightforward to know. I think it's still an open problem. So for the W1P removability, it's just condense P is larger than 2 and P is. And for P is larger than 2, it's just a removable. And this is written, this is also proven by Ntalampekos in his math paper. And for it's just a non-removable. For P is larger than 1 and smaller equals than 2. And this is his invention paper, is tested this paper. And this quasi-conformally removability is also non-removable. This is his invention paper. And we knew that this is just a bit like this. And then for the Sierpinski carpets is maybe much not discussed in this paper, but I just to say here, it's non-removable. And this is by the construction of Ntalampekos and Wu in their Ham's paper. And for the it's also non-removable. Because this one is non-removable. This is also proven by Ntalampekos in the Indiana paper. Of course, this one derives the non-removability of this one. So now we can give the full answer of this removability, not only the quasi-conformal removability, but the Sobolev removability of the gaskets and the carpets.
So one thing that's not known is whether there is a homeomorphic copy of the Sierpinski gasket.
You mean the gasket? I think this one is still an open problem, but Ntalampekos written in his paper that it can use maybe use the same idea to show that for the copies it has a similar result as the gasket. But he didn't show the whole proof, I think. And this is just the brief idea of the proving the W1P removable for P is larger than 2 is about detour property. Since it's not very important it's not showing in this paper, so I can just show a picture like this. It just means that the gamma is just a kind of detour the straight line, and if it has this property, then it can be proven the removability. It's called a detour property. So it means that for each line L, there exists a detour path gamma arbitrarily close to the line and such that the gamma intersects only finitely many complementary triangles. So it's just like this. The gamma is very close to the straight line, but the gamma can only pass through for the finite many complementary triangles. So it is also, in my point, I think it's also very delicate proof to in his messy paper to show the removal. I just take a topic here is to give a whole picture of this story because I think we need to use a brief story of this.
Finally, so this idea is essentially to prove the absolute continuity of lines. That property, and that goes back essentially to John Smirnoff paper where they do something like this. The idea comes from that.
You mean John Smirnoff?
Yeah.
Yeah.
So these people need to use ACA property.
So we use this property to prove ACL.
ACA, and then
And he used this to prove it for the fractal structures, just like Professor Jacobian sign. And then for the most difficult part is for the p is equal to 2. Then it's just I see this to be the Sierpinski gasket is W1T removable if and only if p is larger than 2, because we have shown that when p is smaller or equal than 2, it's non-removable. So actually the main theorem in this paper is the quasi-conformal non-removability. So the main point to prove this non-removability, of course, is to construct the exceptional homomorphism F such that F is quasi-conformal on the C minus K, but not quasi-conformal on the whole C. So actually this is a concrete example, or we can see exceptional homomorphism F. And then there is a natural question, as Professor Jacobian said, that what about the extension to the all homomorphic copies of the Sierpinski gasket? So Ntalampekos read in this paper that he believes this still has a similar structure as the Sierpinski gasket, but actually his construction of the flat plane is very difficult. So I don't know whether it's just the same thing, but I believe this should have some similar thing because the homomorphism didn't have real influence on the structures of his construction. And then let me talk something about the preliminary. The first of all is of course the quasi-conformality on the planar domain. It's just here we use the analytic definition because as we know, then the quasi-conformality has 3 definitions, just like metric definitions, analytic definitions. So here we use the analytic definitions. It's just the operator norm of the differential at z is just the smaller, the square is smaller or equal to the m times Jacobian. We see that f is m quasi-conformal for some m is positive, and the number m is called the quasi-conformal distortion of f. And then since here, this problem is from R2 to R2, or we say from C to C. But only new C to C cannot solve the whole problem. We also need some techniques on metric spaces. Then we need to remove the definition from the planar domains to the metric spaces, because we are considering actually is the metric spaces that are locally asymmetric to the open subsets of R2. So sometimes we call this to be metric surface or metric sphere. Then we say that F is M quasi-conformal if we can localize them, and each localized is the same as the quasi-conformal on the planar domain.
it's a typical definition in the manifolds.
Yes, actually.
We have everything to the plane.
Yes.
Say that again.
And actually, we need the main properties we need here is that quasi-conformal mappings just preserves the null sites. Sometimes we call this losing n condition. It means that F is a quasi-conformal mapping from U to V. Then if A is a measure 0 site, then of course under the quasi-conformal mapping it must still have the measure 0. And then we also need to introduce here, is just the quasi-symmetric maps. Quasi-symmetric maps has a globally control distortion. So it means that for every 3 points, x, y, z belongs to x, then we can just control the distortion by the function eta. So the eta is called the distortion function associated to the quasi-symmetric map. And actually, the quasi-symmetric, in this definition, quasi-symmetric map is quasi-conformal, and as really says that when quasi-conformal composed with the quasi-conformal is still a quasi-conformal. That is also neat in our main proof. Actually, the proof is very difficult, so I can only give some brief ideas of the proof. First of all, we just recall the main theorem. What we want to prove is that we need to construct a homomorphism F from C to C that is quasi-conformally on C minus K, but not quasi-conformally on the whole plane. And then for the brief idea, I can divide it into 3 steps. Actually, the main point is the construction of the flat planes. The first step is just we collapse the triangles to triples continuously, but then it just means that it's not enough because when it just collapses them continuously, it not satisfy the it cannot to make to be a homomorphism. And then we need to construct an abstract surface. And the step 3 is that with the help of Bank linear theorem, we can quasi-symmetrically parameterize this abstract surface and then compose to the mapping we derive from step 1. We just get the exceptional homomorphism as we wish. And after we just construct the exceptional homomorphism, then we just prove the non-removability of the Sierpinski gaskets. And the first step is just to collapse the triangle to the triples continuously. Here, the triangle is just because just the Sierpinski gasket, the complementary components of the Sierpinski gasket contains the infinity many equilateral triangles, just like the left triangle. And then we just collapse it into a triples continuously.
So it just feels grab the circle inside and then we just take 3 points that touch the circle and the triangle and then we just this.
I think they don't have to be in the middle.
Yeah, because actually
This is they draw them. But the general just inside the circle is there and then do this.
yes, actually maybe I could.
Cut the point in this kind. Yes.
Those, I mean, this is just a beginning, so.
Yes, it's very.
Just when because we show what the idea is, kind of collapse of those complementary components, then you get some weird thing, it's not.
Oh, this is because they are both.
Yes, as the equilateral triangles as the complementary components. Here is here is the only you can choose one and then we iterate it for countably many times. So the first thing
You can start the circle, so to the collapse.
no, it just collapse to the triples.
I don't know.
No, for that particular case, it's okay because he has only equivalent.
Yes, yes. So it just means that because if this is a
And when you collapse this everything, you will.
yeah, this is the largest complementary components, and then by the mapping F, we just collapse it into triples. So it means that the center is here, and the center of the 3 sides is all thinking to the center of the triples, and these 3 points is still the to be these points, and then we iterate this, and the construction is very delicate, and we can show that F is equal to identity. F is identity on the unbounded component. Okay, so it means that because there is only one unbounded component, it's just like this.
Maybe draw that the triangle still goes to.
Yes.
No, the big on the right hand side. On the right hand side, and then
You mean this?
well, the triangle's known to that, but the big triangle is still there.
Yes, yes, the big.
Because we never touched the.
Right,
Right.
on the outside, it is an identity, right?
Yes, on the outside of the big triangle, actually, this is still identity, and then
Well, yeah.
Yeah, but the point is, he needs to construct a homeomorphism, which this is not.
and F is injective outside the bounded outside the triangle components. So it means that F can only be chosen to be an injective map or outside the infinity of many triangles. And this collapse is only the for the first, and then we iterate it for infinity many times, then we can get the whole F. But then the main difficulty is to show that F is a uniformly continuity.
May I ask a question?
Yeah.
And what kind of object we end up after the?
Yes, then we can show the picture. It's just like this, because you can see that the blue. Yes, yes, because the red one is the largest triangle, then it just collapse into the triples, the largest triple, and then it's just like the green one and the blue one.
Okay.
Actually, here is just a very abstract construction. And then we can obtain a map that is continuous and surjective, and of course the Sierpinski gasket K is just a mapping to a full Lebesgue measure because the triples has the zero Lebesgue measure. So Fk has a full Lebesgue measure.
Full means positive.
Yes, yes, positive or. And then the second one is the most difficult. It's just to construct an abstract surface. Why we need to construct an abstract surface is that because we get the F from C to C, that it not satisfy the result. Otherwise, this is just we need to construct that is quasi-conformal outside K, and then phi K has a positive H2 measure. Of course, the most important one is that we need to parameterize this quasi-conformal, quasi-symmetrically parameterize this. So it means that S is a quasi-plane. This is actually the most difficult part. We can see that this is a triples and the equilateral triangles. Then we just split it into three parts. And on each of the side, we just we have the 6 sides here, and for each of them, we just connect the rectangles on it and get the flat plane. So actually, this is a very delicate argument, so I can only see the brief idea here. And when the height is chosen small enough, we can show that it is R-close regular and it satisfies the bound linear condition. So we can see the first F is just the polyps, and then the second is that after the B, it's just to the flat plane.
So you somehow look at the transversal component
Yes, yes.
to the three.
But
To make
one question, so the green black triangles and the
Right.
and the brown one, they only intersect at the one point.
Yes, yes, yes.
They don't intersect along.
On the side or something.
Yeah.
Because that's the most difficult part. They only meet at most in one point. And then we can, under this, we can show that there exists the exceptional homomorphism, because we need to use the Bank linear theorem, because the first thing is that we define the C to S. S is the mapping surface we just constructed in the step 2, and then from the maybe this part we use the Bank linear theorem, And the first one is quasi-conformal on C minus K, and this is quasi-symmetrically everywhere, and of course quasi-conformal. Then the whole map from C to C is quasi-conformal on C minus K. But so this is just we need the bulk linear theorem. It means that if the metric space, the metric surface is just R equals 2 regular and homomorphic to the sphere, then it just can be quasi-symmetrically parametrized to the sphere if and only if it's LLC. LLC, it just means that some connectedness is just called linearly locally connectedness for every pair of points. This is the definition, and actually not every metric sphere is LLC. For the basic example, we can imagine such a plane. Because this we can think as a plane, and if we just fold this as here, and here is just y is equal to x squared, and then multiplies the r. This got a plane. This is of course homomorphic to the plane, but it's not the LLC because the here has a cusp point and also cusp axis. Then it not satisfy LLC anymore. So this is very important theorem and has a great deal of proof. Maybe I don't remember who gave the talk about this. And of course, under the after the computation, we just show that we get a mapping because set F is just equal to. And this one is just mapping because K is measure zero, and but the Fk is just give the positive cost of 2 measure. So by the Lucien N condition, we knew that it cannot be a quasi-conformal map from C to C, because if it's from C to C, it must mapping the zero measure zero sides to measure zero sides. This is not satisfied. So this is a construction of the exceptional homomorphism. And the last part I want to talk about is the open problem.
Sorry.
Yeah.
How do you know it's positive measure?
You mean just the imagine is positive measure?
So if you take this tripod things,
Yes, because the treble is just a zero measure.
right, tripod 0, oh, okay.
You just collapse them.
So, oh, it's because it's quite conformal.
Yeah,
The complement of that
Yes,
tripod, so you can think of it as a mapping in the plane or something.
because it's just we just collapse them and get to the flat plane, and the flat plane has size that the complementary components is all shrinking to the trebles. So that is actually very technique to show that it has a positive area, but
So let me just get the logic. You get this mapping from the plane into the surface.
yes,
Now the surface is, if you forget about the tripod things,
yes,
it's basically a bunch of like surfaces glued together.
yes, it is.
So it's like two-dimensional thing. So you use von Kleiner, map it to some
Yeah.
the regular surface, because it's from the two-dimensional to two-dimensional thing.
Yes,
It also preserves two-dimensional measure.
yes,
Oh, I see. So, and because the triangles have zero measure, that means the rest has to have positive.
yes, of course. But it highly depends on the detailed construction. It's not.
Yeah, the heights have.
Yes, the height should be arbitrarily small enough, but it still needs to satisfy the bulk linear construction. So
Right.
it needs to be the most difficult parts in this paper, I think, is to be the construction of the metric surface.
Choose the heights.
Yes, to choose the height, of course, it satisfies the connectedness, the linearly locally connectedness. And in the last part, I want to
I
talk.
was wondering if the open problem should be discussed when we discuss.
Well, everyone has, so maybe we can at the end get together with all the.
No, but he wants to give open problems.
Okay. Well, how about let me finish them fast and then we'll go detail.
Okay.
And then the problem 1 is just if a set is quasi-conformal removable, and is it also locally quasi-conformally removable? This is the essential difference between Sobolev removable and the quasi-conformally removable, because by the united by the partition of unite, we can prove that if a site is Sobolev removable, then of course it's locally quasi-conformally Sobolev removable. But for the quasi-conformal removal, it is not the issue. And I think this is maybe should be the easiest problem from these three. And the second, just to really also mention, is that if the union of two intersecting compact sets is quasi-conformal removable, whenever each of them is removable, this is just like the union of the union of two is just look very easy, but actually I think this is also a difficult problem. And the third one is just to characterize the quasi-conformal removable sites in the dimension 2. And Ntalampekos just also give a definition of CNED sites. And this means that it's just has some relationship between the extreme distance, and we can see that the capacity or modulus. Then he defines the CNED sites, and his conjecture is that the CNED sites is equivalent to the quasi-conformal removal sets in dimension 2. So it's just a countably negligible extreme distance. So you can think that for the countably many point, I'm not sure how to describe this.
So, do you know any D-sets of Alfors and Berlin? Those are the ones which are negligible for extreme of distance.
Yes.
So if you remove them, then the modulus going through them or without them is the same. So it's kind of the same, but it's allowed, the curves are allowed to pass through these sets only count to the remaining points or simplified.
Yeah.
So one good thing is that this thinking, this spatial gives a uniform approach to all the known non-removable or removable sets, like, so it's really good.
Yeah, so Ntalampekos thinks that this is very he conjectured that the CNED sets is just if and only if the quasi-conformal removable sets, and he has made a great deal of works about this. So this is also an open problem 3. So okay, so just thanks for the organization and to give me the opportunity to give an English talk. Actually, I think it's not fluent enough, and actually this paper I still have a lot of difficulties in this paper. Now I can only talk about the brief ideas. Actually, for the delicate constructions, there is still a long way for me to go.
Thank you so much.
And I just learned Armenian today from the internet about the thank you. I'm not sure whether it's true. It's called Shnolaka Lutrion. So
Any questions?
that's really because it's difficult.
I can't do that,
Any specific questions?
Hello, I have a question.
Hi, Eileen.
Because they have the same price,
Yeah. Chengxi, you were talking about W1P removability, correct?
Sorry?
You were talking about W1P removability, correct? For this Sierpinski gasket and Sierpinski carpet, correct?
Yes.
Do you believe that we can do similar kind of things for WKP when K is bigger than 1?
Well, I think this is depends on the fractional Sobolev.
No. We are still in WKP where K is bigger than 1 and integer. So we will not go to fractional setting. So W2P, let's say.
Actually, I don't believe this is a trivial generalization of these results to the W2P, I think.
Okay, okay. Thank you.
Because I think it's highly, because the W1P is related to the quasi-conformal and we can use, yeah, we can use some complex analysis techniques, but I think for the W2P, it might be more, need more things from the Sobolev analysis, then it may make things difficult.
Okay.
So like, I mean, you had think about homeomorphic images, like, I mean, just imagine generalizing this to homeomorphic images.
Yes, yes, yes,
I don't even know where to go with that.
yeah, I think.
This already is so hard.
Yes, I think even for the homomorphism copies of the gaskets, it should be.
Why don't you say quasi-conformal and say how this under quasi-conformal?
Quasi-conformal
It
is.
doesn't make any change.
Yeah, it's still
Yes.
removable.
Yes, yes, because I think
With the
W
bitmaps,
one, one, two is,
Well, I think one example, if you take the Apollonian gasket, maybe.
yes, yes.
But I think that in that case, maybe it's known, right? I mean,
You mean Apollonian gasket?
What is this?
It's just another fraction of,
so it's homomorphic to the Sierpinski
Yes.
gasket, but then you do it with circles.
yes, yes,
So you take 3 circles,
So we remove circles, but not the triangles.
right?
And
The
they
tangent of
somehow,
circles.
Yes, and it's homomorphic to this thing, but I'm not sure if all the possible ways of doing it would be
So
non-removable.
that is a good question. What is the class of equivalence? Yes, what is the correct definition of the class of the equivalence such that if you have a map from the Sierpinski gasket, you element in this class, it's still.
Yeah, because I think the Apollonian
What is
gasket,
this kind of, how you define this?
Yeah.
I think the Apollonian gasket is also the non-removable, if I remember.
So maybe it's like one of the 3 sequencers.
Yes, I think in some survey paper, I think some
Yeah.
survey paper, but
So yeah, another example where it's not known, very interesting, is the trace of Brownian motion in the plane. So that's like, yeah, so it's known that it has alveolar dimension too, but it's not known if it's non-removable or.
Okay, is there any question?
Yes, any more questions? Thank you so much.
Thank you.